Hello guys, welcome to the second part of this tutorial on where we generate input files and pseudopotentials. So for this specifically focuses on the pseudopotentials. So as you can see, we have our calculation is based on the density functional theory and our code is CASTEP code. By default, norm conserving potentials are the ones that are used by CASTEP. The libraries are there. So if you navigate to the folder, you'll find that the default one. So CASTEP will always pick the best pseudopotential based on for your calculation. So I cannot remember where it was, but we have the pseudopotentials here. So yes, we have some of them are here. So these ones are for OTFG. So we have so many things. So normally we have so many types of pseudopotential, but in many papers, I have seen that ultra soft pseudopotentials have been recommended because they need with a lower cutoff energy, you can still get very accurate results. So at the cost, if you don't have a very powerful computer, so you can use USSP, but very high cutoff energy, at some point it will reach a point where the accuracy doesn't matter, just like the Taylor series. At some point, after you get to 4th decimal point or 3 decimal point, it really doesn't matter whether you increase the steps or not. So you can use for C17 and QC5. These are also some of the pseudopotential, but they are very inaccurate. USPP has been recommended in so many papers. So if you go to the CASTEP website, so you find that this is the code that we need to put in our at the end of our input file, the cell file. So block species potential. So you have to put this and specify the type of potential that you want. So for example, let us go to our example. So we go to our example that we did last time. So in this case, we have C19 was selected as the best for titanium. So in this case, for example 2, we want to come here at the param file and change this. We have to reduce this. So we put this at 300 like that. So and then we have to come here. So I have already added these lines. I had previously added them. So and then I want to specify that I want to use QC5. So and then I do the run using my Ubuntu. So I close this, save, and then come here, I run it. Don't worry about this failed part. This failed part, I had forgotten how to put .mpi here. I forgot it, so I want to run this. So once I run it, you realize that CASTEP will select. You see, it has selected QC5 because we have already specified it. So now let us wait for it to finish. So now our calculation has completed successfully. So now we go back, we go and check our generated CASTEP.file. So we see this our report, and then we come down here, and then we see the time taken. That is okay. Okay, time 151. It's a bit faster. So the bulk modulus is 112, almost same to pure titanium. Even we can see it's a bit accurate. As you can see, it's a bit accurate. So it's accurate. So now maybe it's because of the small supercell size, not supercell, the small cell size, only 2 atoms. So now we want to run again. This again, but now using the USP, the ultra soft pseudopotential, not USP, USSP. Yes. So to do this, we must do some few things. So we must come here. So this is an example from CASTEP themselves. So you can get this SI2. So we must add that line. So we can come here, param file, cell file, then we add this. But now we need to add titanium here. Can do Ti and then Ti like that. So, and now we delete these ones. The only thing we are going to copy is to cut is this file, because we want to compare the time taken or even the accuracy. So we want to delete these ones like that. So we want to run this again. We want to run this again. So yes, as you can see, there is this error. We have an error. The reason for this error is because we have called a pseudopotential, which is .usp, which is not located here. Remember, in the other one, we had just written the name of the, we had written just PBE, no, QC5. So if you write QC5, but even if we write PBE here or USPP, it will not recognize it. So we have to go and load that pseudopotential. So lucky for me, I have these pseudopotentials here. So I just write Ti titanium like that. So titanium. So I come and check for titanium. This one. So I copy this. So this will load the PBE, Ti, and then USP. As you can see, here we have USPCC, we have USP, we have various. So I come here, I copy this, and then I hope I have copied it. I paste it here like that. And then this code, that one, I have to come and add it here like that, and then save. So let us run it again and see if we are going to start the calculation. Always check if you have everything. So now I want to run this. So once you see that it's taking a bit of time, it's going to run. And this time, because we have specified the ultrasoft pseudopotential, so it's going to load this from this folder. So you must have this. And PBE is a very accurate. It's a very accurate pseudopotential. We also have PBE sol. So that PBE sol is good for elastic constants for solids. So it's more accurate, but almost the same. So as you can see, we have already specified, so it doesn't need to create another one. So now we wait. So our calculation has completed. It has completed. So sorry about this. I had closed Ubuntu accidentally, so I had to write this again. So now I renamed this file, the one that we created. So now we go to example 2, and now we open our CASTEP file. So I want to do some few comparisons. As you can see, calculation took PB, no, not PB, sorry, I keep on confusing it, but USPP is more accurate. It's way faster. It is way faster and it's more accurate. So as you can see, we almost have the time of calculation. As you can see, we have 88.5 seconds, and here we have 151. So we almost have the time of our calculation. Now, if we come here and check, we can see that the accuracy of the density is a bit lower, but the bulk modulus is almost the same, as you can see. And also we can check the elastic constants, almost the same. For pure titanium is 4.679, so if we round this is 4.68. For pure titanium is 4.684. Here is 2.9. 58 for pure titanium is 2.950 or 51. So as you can see on this, on the other hand, if we look at QC5, you can see we have 2.949, that is okay. But now for the C, that is C, it's a bit lower. So we have that compromise between accuracy and speed. So that marks the end of this tutorial. I hope you've enjoyed it. Tune in for the last part of this video. Yeah, thank you.